Well, hello everyone. I want to just say, hope you guys are having a really good year so far. Happy New Year to you. And I'm sorry about the sudden interruption in our classes. Things have been pretty crazy for me over the past month or so. I've been traveling quite a bit due to some uncontrollable circumstances in my life. And I'm sure things have been hectic for a lot of you probably too. General consensus is that with the coronavirus being prevalent once again, with new strains being identified, things are kind of being thrown into disarray. Like everybody is having kind of a hard time coping with all of these changes. So all I ask is that you bear with me and let's have a really good, a really solid end to this particular class. Have a really good, solid end to our algebra class. So I kind of wanted to start with a review. Maybe just a quick cursory review, algebra at a glance. We're not going to be good at getting super into detail with any of these things, but I want to just review everything we've covered since day one. So what is algebra exactly? A general definition of algebra is taking information that you know and then using it to find information that you don't know right away. There is a distinction between implicit information and explicit information. So for example, if we have an equation like this, it'd be nice if my computer wanted to work. There we go. If we had an equation like this, do we know what x is? Well, we don't know right away, but it's pretty easy to find out. So we would say that this is implicit. This is an implicit solution. The information is there, it's just not really clear. We have to do a little bit of work to get the complete detailed answer to this problem. So let's go ahead and solve this for x. So 2x plus 4 is equal to 8. So what we can do is we can start by subtracting 4 on both sides of the equation. Whoa, I didn't mean to use a pen size. It's that big, my apologies. And I'm sorry if things don't seem quite the way they usually do. I'm not using my normal setup right now. I'm kind of in my default travel mode. Unfortunately, I've been traveling a lot. I'm kind of sick of it by now, but I don't really have a choice. So this is my kind of like my traveling setup. All right, so let's continue. We're going to start by subtracting 4 on both sides of our equation. And you might be wondering, why do we do that? It's because we want to isolate our variable, x. We want to solve the equation, and in order to solve for x, we have to get rid of all the junk surrounding x. And we have an order of operations that would typically help us. We have, please excuse my dear and Sally, PEMDAS, as we're all pretty familiar with by now, parentheses, exponents, multiplication, division, addition, and subtraction. So it's just kind of a simple guide to help us understand what things come first. If we are evaluating something, if we have, I don't know, something like this, whoops. If we have something like this, PEMDAS just tells us the standard order of operations in which to do things. We do everything in parentheses first, and then everything in exponents after that, and then multiplication, and then division, and then addition, and then subtraction. So the thing that's different about something like this, if we're actually trying to solve an equation, whenever we're trying to solve something, we have to take PEMDAS in reverse. So we're not going to start with parentheses and work our way down to subtraction. We're actually going to start with the lowest level and then work our way to the left from there whenever we're trying to solve. Whenever we have something equals something else, we're solving for a variable, we're going to take PEMDAS in reverse. So we don't have any subtraction. After that, though, we do have some addition to do. We have 2x plus 4. So the reverse PEMDAS tells us that we want to take care of the addition before we take care of anything else in the problem. So we have to take care of this plus 4 somehow. We have to get rid of this plus 4. And let's just ask ourselves really quickly, well, math is a game of opposites. Addition and subtraction are opposites. Multiplication and division are opposites. There are many, many more things that fit that paradigm later on down the road, not only in algebra, but basically every math class you'll ever encounter in your academic career. Math is a game of opposites. So we want to ask ourselves, what is the opposite of adding 4 to a number? And that would be subtracting 4. So that's why we want to subtract 4 from both sides of this equation. Our main goal is to just get rid of this 4. So the 4 goes away completely. And then we have on the right side, we no longer have an 8. We actually have an 8 minus 4, which ends up just being a 4. So far, so good. So now that we don't have this 4 anymore, what do we have on the left? We only have a 2x left over on the left side. So we have 2x is equal to 4. So we've already done the subtraction. Actually, sorry, we didn't have any subtraction to do, but we did take care of all the addition. What's after that? We don't have division either, but what we do have is multiplication. We have the m and PEMDAS. If we're going from S all the way up to P, the m is multiplication. So we have to get rid of this multiplication somehow. So we can think of this as doing 2 times a number. We're asking ourselves 2 times what number is equal to 4. So the opposite of multiplying a number by 2 is dividing a number by 2. So I'm going to take this I'm going to take this number times a 2, and then I'm going to divide all of that by 2. And then in order to make sure it's equal, I'm going to do the same thing on the right side. So that's what the concept of equality really means. If we don't do it on the right side, if we only do something on the left, it's no longer going to be equal. In order to preserve this equal sign, in order to prove that this really is equal on both sides, we have to do the same thing on both sides of our equation. So the 2's go away, nice and easy. So that means our result is going to be 4 over 2. And remember that fractions are just another way of expressing a division problem. Fractions are just a ratio. We're just comparing the quantity of 4 with the quantity of 2, which can be thought of as 4 divided by 2. So how many times can 2 go into 4? That would be 2. Yay, we found our solution. Let's go ahead and write this. So we have our solution is x equals 2, and we're going to call this the explicit solution. And you might be wondering what explicit and implicit mean in an algebra context. So implicit refers to a situation where the information is there, but it's not clear. It's not stated outright. And then explicit is kind of the opposite. The information is completely stated outright, and it's completely easy to see what it is. So the solution is the same in both of these, but with the one on the right, it's perfectly clear. We know exactly what it is, and it's not so clear on the left. So that's just a quick explanation of implicit versus explicit solutions. Whoops. So algebra is very, very vocab intense. We're going to have to review a lot of vocabulary words just so we can understand what's going on in certain types of problems. And it's not something that's specific to algebra. It's something that you're going to encounter many, many, many times in every single one of your math classes. Math is very vocab specific. You have to be able to read a problem, take a look at some keywords, take a look at some clues, and then understand exactly what the problem is asking for. And sometimes it's not so easy. Sometimes it seems like they're making things intentionally difficult on purpose. So I'm hoping in this video, I can give you guys some tips, give you maybe a few pointers you could use to help make sense of a complicated problem where the thing that they're asking for may not be completely clear. So I know a lot of people hate word problems. Word problems tend to get a lot of hate in algebra. They have kind of a level of notoriety, if you will. And that's just because they tend to be a lot more difficult. And back to the implicit and explicit thing, in a word problem, they don't exactly tell you directly what they want. You have to read through the problem maybe a few times, pick up on some clues, and then see if you can convert it into algebra. And algebra is actually a language. A lot of people don't consider to be algebra a language, but it is definitely a language. Kind of like Spanish or Greek or French or Chinese. It has all of the same things that a normal language would have. It has syntax. It has its own vocabulary. It has its own symbols. It has its own method of communication, both written and verbal. So algebra certainly is a language. And the goal of this class, the goal of my Algebra 1 class that I teach, is to make sure that all my students are comfortable and fluent in the language of algebra. Because if you're not fluent with algebra speak, you're going to have a really hard time down the road when you take geometry and algebra 2, trig, pre-calc, and especially if you go up to calculus. We're going to want to have a really, really solid understanding of the language of algebra. We're going to want to be able to communicate really, really fluently with other people and communicate results to others. So it's really important for us to understand the language of algebra. So let's quickly touch on a few word problems, and then they will give us a really good amount of practice to convert a problem into English, or sorry, I meant to say convert a problem from English into algebra language, and then we can effectively solve and find the solution that they're asking for indirectly or directly. So I found a pretty interesting word problem. This comes just from the internet. I Googled algebra word problems, and this is what came up. So we know that the sum of two numbers is 84. One of them is 12. And I'm going to go ahead and write this. Example 1. Sum of two numbers is 84, and one of them is 12. I guess I should use the numerals instead of the written version. 12. Oh, 12 more than the other. What are the two numbers? Let me spread this out a little bit. So let's maybe just talk about this real quick, see if we can make sense of it, and then see the best way we could possibly convert this into algebra language, the fastest and the most efficient way to translate it, if you will. But before we do that, I'm going to erase this PEMDAS. We don't need that anymore, at least not now. So algebra has certain words, certain phrases, certain symbols that can be translated into other words and phrases and symbols. So let's talk about what the word of means. Of in algebra always means multiply. But before that, let's talk about the word sum. What is a sum? The sum is the answer of an answer to an algebra problem. Or sorry, I don't know what I'm saying. The sum is an answer to an addition problem. And I kind of just want to write these off to the side of the page so that we have a really good understanding of what's going on in the problem. So I'm going to create some definitions. Sum would be the answer to an algebra problem. I keep saying algebra. I meant to say addition. Sorry about that. Don't know what's wrong with me today. The answer to an addition problem. And then what else do we have? We have the word of. Of means multiply. And then we have two numbers. We know what those are pretty well. What does is mean? We know what it means in basic English communication, in basic English context, but in algebra, what the heck does is mean? Well, you may not know it, but is also has a really special meaning in math. Is equals. So far, so good. And then we have, and one of the numbers is 12. So we have is again, that's equals. 12 more than the other number. So we know what more than means. We're just comparing two quantities. One is going to be more than the other. If they're not equal, one has to be more than the other. And then what are the two numbers? So it kind of tells us right away what we're trying to do. We're trying to find the two numbers for which all of these statements are true. We could just pick random numbers. We could maybe pick 1 and 2 and see if they work. So the sum of 1 and 2 is not 84. We're way, way off. So some people might be of the mind to just sit here and guess and check. Guess number after number after number. You'd be here for a really long time. So we want to find more direct ways of finding the numbers. Guessing and checking is definitely not efficient. So we want to steer away from that. We want to convert this into algebra, solve the problem, find the solution in algebra language, and then translate that solution into an English language so that we're able to properly communicate our results to other people depending on their level of understanding of math. Our goal is to be able to communicate our solutions to just about anyone and use the algebraic and verbal tools to fit the description of the solution to fit whoever we're talking to, if that makes sense. So let's go ahead and mark some things up. I'm a visual learner myself. I found out it really helps to highlight certain things and identify the significance of them in the particular problem. So for example, we have the sum is right there. We have the word of means multiply. And then we also have is. We have an is here. We have an is right there as well. So now that we have this groundwork laid out for us, let's see if we can begin converting this into algebra language. Assuming my computer wants to work. You know, sometimes I have to threaten to throw it out the window and then it suddenly starts working, but it looks like it's working fine now. So we know that the sum of two numbers is 884. So we know what the sum is. Sum is just the answer to an addition problem. My grammar is atrocious. I don't know why the S is there. Didn't mean to put that there. Answer to an addition problem in the singular is what I meant to say. And then, of course, it erased part of it. Computers, They're supposed to make our lives easier, but oftentimes computers just make our lives more complicated than they need to be. So hopefully that's the end of my technical issues for the day. So we know that the sum of two numbers is equal to 84 because the is equal. We know is means equal. And we know that the sum of two numbers, well, in this case, we're not going to use this definition of. This mainly just applies to multiplication problems, multiplication of fractions specifically. So we're actually going to neglect this definition of multiply for this particular problem, and then we're going to be using it a little bit down the road, but it doesn't apply too much with this one. So So we know that the sum of two numbers is 84. We don't know what the numbers are. So there's got to be a way to write a number sentence to write an equation, considering we don't know what the numbers are. We need something kind of like a placeholder just to identify that we recognize that they are two-digit numbers. So let's use just variables. Variables work really, really well in a situation like this. Sum of two numbers. The numbers are x and y. We don't know what they are, but we're going to find out. So that's one equation. And then we have another is, which means that's another equal sign, which means we're going to have a second equation. One of the numbers. Now, it doesn't really matter which one we pick to be x, which one we pick to be y. I'm just going to go with the first one being x. So one of the numbers, call it x, is 12 more than the other number. So how do we write 12 more than the other number if our first number is x and our second number we have is y? So how do we put this into algebra notation? How do we write 12 more than the other number? So we know that the other number is y, and we know that x has to be 12 more than y. So whatever y is, we're going to increase that by 12. Very nice. So we have our two equations. Let's see if we can solve it. So what does it mean to solve an equation exactly? To solve an equation, it means to find the explicit solution. Because right now what we have is we have the implicit solution in terms of two distinct variables, in terms of x and y. So our goal is to go from having this implicit solution in terms of two variables and two equations to having just one single explicit solution for x and then one simple explicit solution for y as well. So let's decide what might be the best plan of attack to figure out what the solution is going to be. So I'm looking at the top equation. I can see that we have x is equal to something in terms of y. So what we might want to do is solve the bottom equation for x. And if you guys remember from, I think it was a couple months ago when we were dealing with problems like this in algebra, what we're doing right now, this is a system of equations, a system of two equations and two variables. We have two equations, we have two variables, the variables being x and y. So the thing about a system of equations is that if x is equal to 3 in this top equation, x also has to be equal to 3 in the bottom. We can't have two different x values. Whatever x has as a value on the top, it also has on the bottom. And then same thing for y. Whatever value y has for the top equation, it has to have the exact same value for the bottom equation. So now let's go ahead and see if we can solve this. So I see that we already have it solved for x. We have x equals blah, blah, blah. What I want to do is I want to take the bottom equation and make it into something that looks really, really similar to the top. I want to convert this bottom equation into x equals blah, blah, blah as well. So how do we do that? How do we get rid of this pesky y that is on the left side of that equation with x? So we're adding y. The opposite of adding y is going to be subtracting y. So we're going to subtract a y here, subtract a y on the right side as well. So it works out really nicely because y's go away. They cancel out. And what we have left over is 84 minus y. And this is exactly what we want. And the reason why it's really, really nice to have this, because we have x equals something, we have x equals something else. And because we know that in the system of equations, x has to be the same value on the top in the top equation as it is on the bottom, that means that if x is equal to something and x is equal to something else, that means the something has to be equal to the something else. That right there is something called the commutative property of equality. The commutative property states, for example, if a equals b and b equals c, then we know a is equal to b, which is equal to c, which means that the something we had at the beginning is equal to something we have at the very end. So we can eliminate the b and state outright that a is equal to c. And that's something called the commutative property. Commutative property. And it's the exact property that we want to use in this problem. So we know x is equal to one thing. We know x is equal to another thing, which means that the top thing has to be equal to the bottom thing. In other words, we have 84 minus y equals y plus 12. And it's the commutative property that tells us that. So now what we want to do is we want to see if we can solve this for y. It's really, really nice having just one variable. If we have two variables or even three, it is pretty tough to find what the variables are. It's not exactly easy to solve, but with just one variable, pretty easy, pretty simple. So let's go ahead and isolate the variable y. Why do we want to isolate that variable? Because if we isolate it, it would give us the explicit solution. Right here in this equation that we just created, this is the implicit solution, and it doesn't really help us all that much. We want the explicit solution. So let's go ahead and find the explicit solution by solving for y. So in order to effectively solve for y, we have to move y completely to one side of the equation, make sure all the y's are together, and then get rid of all the junk surrounding y. So let's start by moving all the y's to the same side. We have a negative y on the left. We have a positive y on the right side. So I want to go ahead, I want to add a y to both sides. And the reason why I want to do that is to completely get rid of a y on the left side. We no longer have any y's whatsoever on the left. And let's go ahead and update this. So in algebra, there is a constant need to update your equation based on the steps that you've previously completed. What I mean by that is we want to write the new version of this after we've added y. We want to write the updated version of our equation after we've added y to both sides. So the updated version of the equation would be 84 is equal to, well, we have y plus y. How the heck do we write y plus y if we don't know what value y is? Y is a variable. A variable is just a container that holds a number. We don't know what the number is just yet, but we're close to finding it. So how do we express y plus y without knowing what value it contains? So we can think of this as having one thing plus two things. Sorry, got a bit ahead of myself there. I meant to say it's like having one thing plus one thing. So we know that one thing plus one thing, of course, gets us two things. In this case, we can tell that the thing in question has to be y. So if one thing plus one thing is two things, one y plus one y is going to be two y. So we're just doing one thing plus one thing, and then the thing in question is just y, so we have 2y. And then we still have that plus 12. And remember, our goal is to get rid of all of the junk surrounding y. So we have a y right there. We have to get rid of all of this junk. So we have y times 2, and we also have a plus 2. So now this is when we have to go back to the reverse addition of PEMDAS. So instead of starting with P and ending with S, we're actually going to start at S and work our way up in reverse until we get to the very last step. So the very last step of PEMDAS is subtract. And we don't really have any subtraction going on. So we're going to move up to A here. Actually, I shouldn't have erased that. Looking back, that wasn't the smartest idea. So I'll write it again. We don't have any subtraction, but what we do have is we do have addition. The A is addition. We do have some addition we want to get rid of. So the opposite of adding 2 is subtracting 2. We're going to subtract 2 on both sides. So then this goes away completely, which is really nice. What we have left is just 2y is equal to, it's no longer going to be equal to 84. What it's going to be equal to is actually 84 minus 2, which is 82. So now we have 82 equals 2y. And now we're really, really close to finding our answer. We've already done the addition. Looking at the updated version of our equation, we have 82 is equal to 2y. I don't really see any division there whatsoever. We have no addition. So we're going to eliminate the d in that. Now we have multiplication. We do have some multiplication we want to eliminate. But before we do that, I'm going to write the equation right here. I'm going to just copy it down, give ourselves a little more room to work. But I'm going to reverse it. I'm going to call this 2y equals 82. I'm just switching the order to make it a little easier to understand what the solution might be. It's perfectly valid. If 82 is equal to 2y, it means 2y is also equal to 82. So you can switch the order at any time without consequences. It's still the same equation as it was before. So now how the heck do we get rid of this 2y? Or how do we get rid of the 2 in 2y, leaving only the y? So we have 2 times a number, trying to find out what number we multiply by 2 to get 82. So we're going to employ this m part of PEMDAS. So the opposite of multiplication, of course, is division. So we're going to divide both sides by 2. Nice and easy, the 2 to go away. Yay, we only have a y left over. I sounded really excited there for a second. Don't know why. But we have y is equal to 82 divided by 2. So let's think about if this were just 80 divided by 2. 80 divided by 2 is 40. And then we have this 2 left over we have to deal with. So then what if we have just 2 divided by 2? 2 divided by 2 is 1. So we have 80 divided by 2, which is 40, plus 2 divided by 2, which is 1. So we have our answer, which is 41. So this is the explicit solution. Y is equal to 41. That was fun. That was really rewarding. I hope you guys had as much fun with that as I did, but we're not quite finished yet. We found only one of the numbers. They want us to find both of them. They ask, what are the two numbers? They don't expect much of us, do they? So we've already found one. Now what we have to do is we have to go ahead and find the other number. We have to find x this time. So you might know that at this point, after having found y, x is so much easier to find. It's so much easier to find x now that we know what y is. We don't have to use any special algebra rules or any trickery to find y. All we really need to do is take our original equation and plug in values wherever they're appropriate, except what happened to my equation? I think I must have erased the very first equation we had. So I'm going to just rewrite that. The sum of two numbers is 84. Sum means the answer to an addition problem. So I'm actually going to type this. The sum of two numbers is 84. So that would be x plus y is equal to 84. So the good news is, here, let me color code this. I'm definitely a visual learner, so please indulge me while I color code all of this stuff. So we know that y is equal to 41. There's a y, and there is also a y right there. So I'm going to replace y with a number because y is a variable. A variable is just a container that holds a number. And that number in particular is 41. So we have x plus, no longer x plus y, but we have x plus 41 because y is 41 equals 84. So now we're going to do the reverse of PEMDAS just one more time. We have a number plus 41. We have to get rid of the 41 in order to find what number x has to be in this situation. We're trying to go from this implicit solution to the explicit solution. So according to the rules of opposites in algebra and math in general, we want to, the opposite of adding a number is subtracting a number. So let's go ahead and subtract 41 on the left side and then go ahead and subtract 41 on the right as well. So what do we have left over? We have just a plain old x by itself chilling on the left side of the equation. And then what do we have on the right? If we do just this simple subtraction, that won't take too long. We don't have to borrow anything. This would just be 43. Yay, we found our other solution. So we know y is 41 and we know x is 43. And is that what they wanted? Yeah, that's exactly what they wanted. So actually, we could just leave it like there. We can leave it right there. We don't really have to do anything special. So there are some problems that refer to things in real life. So I don't know if we're going to solve this equation, but I want to read it real quick so you guys have a really good understanding of what I mean by converting your answer into a normal, non-mathematical context. So for example, I'm going to just read this example problem I found on the internet. So Jane spent $42 on shoes. This was 14 less than twice what she spent for a blouse. How much was the blouse? So actually, this sounds like a lot of fun. I think we should do this one. I don't know about you guys, but I don't think I could not do this one. I feel like we have to. Not only is it a lot of fun, but it'll help us understand the problem, and it'll help us understand the process of solving algebraic equations much easier and translating from English into algebra. So we have the fact that she spent $42 on a pair of shoes. That's about how much I spend on shoes every 10 years. I'm pretty cheap. And then we know that this is $14 less than the cost of a blouse. And personally, I've never spent money on a blouse, so I can't make any stupid comment, any funny comment about that. But let's continue, shall we? We know what the pair of shoes costs. We know that the pair of shoes cost $14 less than the blouse. How much was the blouse? So let's go ahead and see if we can convert this into algebra language. We have something in English. We want to translate English into algebra. We want to create an equation based on this information given to us in English. So the first part's pretty clear. The second part, though, the second sentence tells us that the pair of shoes costs $14 less than the blouse. So let's create some variables. So S is the cost of a pair of shoes. We're given that information right away. That looks too much like a 5 for my liking. Whoops. I want to rewrite that, make it clear that that's an S and not a 5. All right, there we go. We know that the pair of shoes cost $14 less than a blouse. So if I'm going to use the variable b to notate the cost of a blouse, then that tells us that shoes, the blouse is going to cost whatever the pair of shoes costs plus $14 more. So let's go ahead and see if we can find the cost of the blouse. So it may not be clear right away exactly how to do that. It may not be super clear how to take two equations, use them together to get the solution. So what I want to do is I want to take this s is equal to 42, highlight it in green, and then I also want to highlight any other place where I see this information also in green. So I see that right here. I see that we have an s in this equation, and then also we have an s on the right side. So we're going to do something called the substitution property, which tells us that whenever we know that s is equal to something, and we have s is in this side of the equation, we can replace this s with 42. We know s is equal to 42, so we can just go ahead and replace s with 42. That's the substitution property. Very, very widely used in math. So now all we have to do is a simple addition problem. We have the cost of a blouse is going to be 42 plus 14. That gets us $56 for the cost of a blouse. So now let's talk about how to convert this back into a normal English context, because we have our answer in terms of algebra. Algebra language, we have an equation. Let's see if we can just convert that back into English. So what does B represent again? B is the cost of a blouse. And I guess if I wanted to be proper, I should put the $sign there. So let's go ahead and translate this back into English. Let's translate this algebra solution into English. So let's go ahead and write this. We have the cost of a blouse is $56. Huzzah. And that's all we really wanted to do. This is exactly how we take an algebra solution, a solution in algebraic language in the form of an equation, and converting it into English. So it requires a fair bit of information about the problem. It takes reading it a few times to pick up on clues. And we know that because B is the cost of a blouse, we know that the blouse has to be $56. So those are just the basics of solving and translating the problem and the solution to and from algebra, to and from English. So I feel like that gave us a pretty good understanding of how to do this kind of a problem. So I was hoping that, I'm not sure how much time I'm using so far, and I apologize, I should have been timing this, but I think there's just one more topic I'd really like to discuss in this video, and I'd save the rest of it maybe for another video. So I want to cover the basics of solving equations, solving quadratic equations. I feel like by this point, we're all really, really good with solving simple linear equations and solving systems of linear equations, but I really want to talk about solving quadratic equations, solving and graphing quadratics. Quadratic equations, what are they? So a quadratic is just another way of saying a quadratic equation. So whenever you hear someone saying solving a quadratic is the same thing as a quadratic equation. So let's talk about what a quadratic really is. What is a quadratic? So a quadratic is anything involving a variable to the second power. X squared is a quadratic. Z squared is a quadratic. X to the third power plus x squared minus 5x. Here, I want to make check boxes so we can identify what's a quadratic and what's not a quadratic. So a quadratic is something where the highest power is 2. So let's talk about what powers are real quick. In just a simple monomial like this, x squared, it's a monomial. Let's review some of the vocabulary real quick. So x squared is a monomial. It's a type of polynomial, and I just realized I can't spell, which might have problems later down the road. Monomial. Hopefully I spelled that right. So mono means one. And that's from Latin. You guys might know that math and a lot of academic disciplines are peppered with lots and lots of Latin. A lot of our math terms are based on Latin. So it's good to have just a basic understanding of what all these Latin root words mean. So for example, mono means one. So a monomial is something with one term. And eel, I mean, that's not officially the Latin word for term, but mono is definitely the Latin word for one. So this would be monomial. Another Latin word for one would be un, the un prefix, kind of like how uno is Spanish for one. Spanish is a Latin-based language, just like English, just like French. Un is one. The word unit means one. A unicycle has one wheel. So un and mono are both Latin prefixes that mean one. So a monomial has one term. And remember, the terms are the things that are separated by pluses and minuses. So if we have x plus 2 minus y plus z minus 4 minus 2x, maybe 2w. Let's see how many terms this expression has. So we have 1, 2, 3, whoops, I didn't mean to do that. 1, 2, 3, 4, 5, 6. You might be wondering why this is just one term. Well, 2w, they are part of the same term. So the terms are things that are separated by pluses and minuses. 2w is a term all on its own. It's a complete term by itself. So what we have here is 6 terms. So a monomial has just one term. So now let's talk about what the degree of, or actually before we even talk about degree, let's talk about the concept of a polynomial. So a monomial has one term. Binomial has 2 terms. Why is that? Because the root word bi in Latin means 2. A bicycle has 2 wheels. Our government is a bicameral legislature, which means that it's split up into 2 houses, the Senate and the House of Representatives. I'm sorry, it's been a while. That might be completely wrong. So I'm just going to stick with a simple one. A bicycle is 2 wheels. So a bicycle has 2 wheels. A binomial has 2 terms. That's really embarrassing. I shouldn't have even tried that. Binomial has 2 terms. So if we wanted to quickly identify a binomial, 2 minus y is a binomial. Y plus z is a binomial. 4 minus 2w. These are all binomials. They all have 2 terms, so they are all binomials. A polynomial, poly means many. Polynomials have multiple terms. So a binomial is a polynomial. So same thing with a trinomial. A trinomial has 3 terms. And then after trinomial, we don't really have a special word reserved for 4 terms or 5 terms or 6 terms. After trinomial, we just generalize it with polynomial. So binomials, trinomials, and every other nomial after trinomial, they all just kind of fall under the umbrella of polynomials. They're all polynomials. They all have multiple terms. So now let's talk about what the degree of a polynomial is. So the degree of a polynomial is going to be the highest power that's present in the polynomial. Highest power you can see. So for example, in this one, we only have one term. We only have one power, one exponent. And I just want to maybe add an aside to that real quick, maybe clarify that a little bit. So power is another way of saying exponent. So whenever we talk about power, power is just a fancy way of saying exponent. So something with the second power is going to be something with an exponent of 2. So we have our exponent is 2. which means we consider this to be x to the second power. And then another word for that is x squared. Or another way we can write that would be x times x. So this is x to the second power. So then the degree is going to be the highest power, the highest exponent present in any polynomial or monomial. So in this case, we only have one exponent, so we have a degree of 2. In something with an highest exponent of 2, that's going to be the degree. So our degree is equal to 2. The degree of this monomial is 2. So let's give a rigorous definition of what a quadratic is. I said rigorous, it actually probably won't be that rigorous at all. But let's have a good understanding, a good base of foundational knowledge to build on. So let's say that the degree of we have the degree of a polynomial already. So a quadratic, let's define what a quadratic is. It's an algebraic expression with the degree of 2, which means that the highest power present in the polynomial or the expression is 2. So that's what a quadratic is, something with a degree of 2. So if we have an exponent anywhere that's higher than 2, then the thing we're looking at is not a quadratic. So let's take a look at some of these I have over on the side of the page. So we have x squared. X squared has a degree of 2, so this is a quadratic. We have z squared, that has a degree of 2. This is also a quadratic. So now let's talk about this next one. We have x cubed plus x squared minus 5x. So let's see if we can find what the degree of the polynomial is. So right away, whenever we have something like this 5x right here that doesn't have an exponent, there's always going to be an invisible 1. 5x to the first is equal to 5x. Whenever there's no exponent, there's automatically just an invisible 1 floating there. So let's see if we can find what the highest exponent is going to be. So we have 3 exponents. We have this 1 that's invisible. We have a 1, we have a 2, we have a 3. Those are all 3 exponents we have in this expression. But what is the highest exponent? So I can see that the highest exponent in this expression is 3, which means that the degree of this polynomial is 3. Here, I'm going to type it. Don't want you guys to have to suffer through my cruddy handwriting. The degree of this expression is 3. So that means it's not a quadratic. In order for it to be a quadratic, the degree must be 2. So something with a degree of 3 can definitely not be a quadratic. Yoink, that's not a quadratic. And then we have this last one. So this one is kind of tricky. If it looks like I'm trying to trick you, it's because I am. We have a degree of 2, right? That makes it a quadratic, doesn't it? Well, no, and let's talk about why. If we have x squared, there's nothing we can do with that. We don't know the value of x. We can't simplify it in any way. We can't put a value in for x. This x would have a degree of 2. But with this one right here, 2 to the second power does have a clear, distinct value. This is something we're able to find really easily. We know 2 to the second power is just 2 times 2, and that's equal to 4. So let's rewrite this. Let's simplify it. So this is equal to 4 plus x. So now, instead of going with this first version that was given to us, we're going to be going with the completed version. They are equal to each other. They look different, but they are certainly equal to each other. So we always go with a simplified one to make more sense of the problem at hand. Let's see if we can identify the degree. So a degree is something that strictly accompanies a variable. So we don't consider 4 as having a degree. We do consider this x, sorry, not degree, I meant to say exponent. So we don't consider the 4 as having an exponent. This x, though, remember that whenever we don't have an exponent with a variable, there's automatically an invisible 1 chilling there. So the highest exponent we have in 4 plus x is a 1. So that has to be our degree. The degree is 1. So is it a quadratic? Well, for it to be a quadratic, the degree has to be 2. We have a degree of 1, which means this thing is definitely not a quadratic. So we found out that we have two quadratics. We have two things that are not quadratics. We've given kind of a rigorous definition of what a quadratic is. We've talked about some definitions. We've talked about what the degree of a polynomial is. We've talked about just basically what a polynomial is. It's an expression with multiple terms. We've talked about monomials. We've talked about binomials. And I feel like this video is running kind of a bit long. So that being said, I don't really want to get into operations on quadratics until the next video. So keep an eye out on the YouTube channel for the next video. The next video is going to deal mainly with solving and graphing quadratics. We're going to be learning all of these cool things, all of these operations we can do with quadratics, and the power they have when you're solving really complex problems. They are a really powerful and really great problem-solving tool to have in your arsenal. So keep an eye out for the next YouTube video. It'll be coming out pretty soon. So that being said, thanks for stopping by. Hope you found this exciting and useful, and I'll see you next time.